I'd like to start the session on differential, impossible differential, and neural distinguishers. This session has 4 talks. The first talk is about the paper entitled Tighter 12 Bounds for Zulu. The authors are Silvera Mera, Yuan Diamond, Gilles Van Asche. The speaker is Silvera Mera. Please give your talk.
Thank you for the introduction. So in this work, we improved bounds for linear and differential trails in Zudo. So Zudo is the cryptographic permutation at the core of the authenticated encryption scheme Zodiac and the DEC function ZUF. Bounds for Zudo have already been proved by its authors. So they developed a dedicated tool called ZooTools that implements what we call the trail core tree search. So the program scans the space of all trail cores for the desired number of rounds and up to a given target weight, and it does it in a tree-based fashion. In this work, we improved this tool with some optimizations to get better lower bounds for the weight of trails. And we also discuss actually some special families of trails that allow us to provide also upper bounds. And in this presentation, I will only focus on differential trails, but our analysis covers also linear trails. Okay, so Zudo operates on a three-dimensional state that we can see as 3 parallel planes of 4 lanes each of 32 bits. The permutation has a classic iterated structure where all rounds are identical except for the round constants used. And the number of rounds depends on the application. So in Zodiac, we have 12 rounds, and in ZUF, 6 rounds. The run function is composed by 5 steps. So first we have the mixing layer theta. That is a column parity mixer that guarantees good average diffusion. Then we have row west, that is a plane shift operation. Iota, round constant addition. And then we have the nonlinear layer key that is like in Ketchak. We can see it as the parallel application of 128 S boxes, each operating on 3-bit columns. And finally, we have row east, that is another plane shift operation. So I wanted to introduce the representation of the state we use in this work, because in this presentation, because there are many pictures. So we look at the state from the top. So on the right, we have the 2-dimensional representation that we will use. And we use the convention that, so each cell here represents a column. And we use the convention that an empty cell is passive column, so a passive S-box, while a color cell is an active S-box. And we also encode, like depict the value of columns by using 3-bit integers. So for instance, 1 means we have only 1 active bit at the bottom plane, while 7 means all the 3 bits in the column are active. Okay, so to represent trails in Zudo, we first rephase the round function by grouping together the linear steps in a linear layer that we call that we denote by lambda. And we depict the trail with this by specifying both the differences at the input of the linear layers and at the input of the nonlinear layers. I recall that the weight of a differential is defined as minus the logarithm of its differential probability, and the weight of a trail is the sum of the weight of the differentials over the nonlinear layers in the trail. So if we look at the S-box in Zudo, we see that the weight is 2 for any valid differential. So this means that the weight of the trail is fully specified by the number of active S-boxes in the trail. That is the number of active columns. So with this NC, we denote the number of active columns of a difference in the trail. Actually, So if the trail is valid, and if we look, for instance, at this differential over key, the number of active columns is in B0 is the same. So at the input of key is the same at the output of key. So we can actually rewrite the weight of the trail in this way. And with this expression, it becomes quite evident how the weight of the trail is independent of the actual value of the differences A0, B0, and AR. So actually, in other words, all trails that share the sequence of differences from A1 to BR minus 1 and differ only in AR and the first two differences actually have the same weight. So the class of this trail is what we call a trail core. And this means that to prove bound, so we don't really need to build all trails, but we can actually restrict our search to trail cores. And this is good because we can then avoid two nonlinear layers. And this has a significant impact on the performance of the tool. So concretely, to build trail cores for the desired number of rounds, we start from 2-round trail cores and then we extend them. In this work, we focused on optimizing the extension step. So I'm not going to explain the 2-round trail core generation, but you can find it in the original Zudu paper. Okay, so for extension, so this is our trail core. And on top, I depict the contributions to its weight. So we can extend this trail core in two directions. So in the backward direction, this means that given the difference A1, we need to build all the differences B0 that are valid at the input of key. And then we map them through the linear layer, at the input of the linear layer. And we update the weight accordingly by adding the weight of A0. And similarly, we can do forward extension. So actually, so key has degree 2. And this means actually that the set of differences, B0, for instance, forms an affine space. And the dimension of the dimension of this affine space is actually the weight of A1. And similarly, for forward extension with the space of differences AR. Now, this affine space, since key acts on each column independently, these affine spaces can be built as a combination of the affine spaces over the columns, so over the S-box. In this table, we give a representation of these affine spaces. So here we have all possible differences at the input or output of key. And on this right side, we have the corresponding affine spaces represented as with an offset O and two basis vectors. And we can notice like every offset has only one active bit and basis vectors can have one or two active bits. So if we look at next to an example on the whole state, so we have this difference A1 that we want to extend in the backward direction. We have here 7 active columns. And this is a representation of the corresponding affine space. So for each active column, we have 1 bit in the offset. So the offset will also have 7 active columns. And then we have for each active column, 2 basis vectors for a total of 14. And now if we look back at our extension, actually when we do extension, the weight depends on the value that we have at the input of lambda. So we actually need to explore this space. And we can do it because, so since lambda is linear, we can get simply a representation of this state by applying the inverse of lambda to the offset and basis vectors of the space B. So concretely, we generate differences directly at the input of lambda. So if we do this, so this is the same example. If we apply the inverse of lambda to the offset and basis vectors, this is what we obtain. And yeah, the only thing I wanted to show here is how dense these states are. So we have many active columns. Okay, so to explore this space, we see its elements as nodes of 3, where at the root we have the offset, and then all nodes can be obtained by adding the offset and a linear combination of the basis vectors. So for instance, if we take this node given by the offset plus the vector v1, we can obtain all its children by adding the other basis vectors. And so since we have seen in the previous slide that these basis vectors are very dense, so it means that when we add v2, maybe a column that was active in this node can become passive in this other node, in the child. And since the weight depends on the number of active columns, then it means that the weight of this node can be smaller than the weight of its parent. So this means that when we are traversing our tree, if we encounter a node whose weight is already above our target, it doesn't mean that this is also for its children. So we still have to explore the children, all the descendants actually of the node. But we would like our search to be efficient. So we would like to prune the tree as soon as possible. So we need to define a lower bound on the weight of the descendants of a node. And to this end, the concept of stable bits was introduced in Zudo, in the Zudo paper. So stable bits are the bits of a node that have the same value also in all its descendants. And we have a stability mask that is just a state encoding of stable bits. So the idea is that if we take a node, in a node, we take only the stable bits, then the weight of the state with only stable bits will provide a lower bound for all descendants. Because the columns that are active, let's say the stable bits identify columns that will always remain active. So the idea is that when this lower bound is already beyond our budget, then we can safely prune the tree. So now the question is, how can we define good stability masks so that the number of stable bits grows as quickly as possible with I? And to give you an intuition of how it works, so we look at the first stability mask definition given in the Zudo paper. So this is the idea. We can see our basis as a matrix. So each column represents a basis vector. And what we can do is to sort of triangularize this basis so that for each basis vector, we have a bit that we call pivot. That is the smallest active bit in the vector that is passive in all following vectors. So we can define the stability mask as all the bit positions smaller or equal than this pivot bit. Okay, so if we apply this definition to our example, this is the sequence of stability masks that we get. And we can see that with I, we always have, so the sequence of stable bits increases by 1. So we aim at doing better than this to have a more efficient pruning. And this is where we introduce our optimization. So first of all, we notice this. So this is an example of the triangularized basis. So we can observe that there are, so for instance, if we focus on this basis vector, we can see, and this bit, so this bit is passive in all following basis vectors, then this means that as a matter of fact, the value of this bit won't ever change when we add the new basis vector. So we can consider this stable. So we introduce this new definition of stability mask as the end of the complement of all basis vectors that we can still add to a node to generate its descendants. So if we apply this new definition to our example, this is the new sequence of stability masks that we obtain. And we can see how the number of stable bits grows already more quickly than before. But we actually would like to do even better than this. And to give an intuition of how our idea works, we can focus on this example. So this is one basis vector of our basis, and this is its value before lambda. But if we look at the intermediate values, so through rho west and theta, this is the value that we have at the input of theta. And we can see that this basis vector has a number of fully passive columns and fully active columns. So I don't know if you see, but all these purple columns are have value 7. That means that all the 3 bits are active. So the idea is, instead of stabilizing one bit at a time, we can stabilize a full active column. So we do a triangularization where we stabilize one active column. And the idea is then that the 3 bits of the column are mapped at the input of row east to 3 different columns, contributing 6 to the weight. We also introduce a number of other, not optimization, but observations to make this as effective as possible, but I'm not going to describe them. All in all, if we apply these optimizations to our example, this is what we obtain. So if we look at the sequence of stable bits, we can see that it increases by at least 3 for each I. And this is the optimal result we wanted. So this optimization allowed us to make our tree search much more efficient. And so it allowed us to scan bigger spaces of trails and achieve better bounds. So in this table, I'm reporting previous known bounds. And here on the right, we have our new bounds. So for instance, for 4 rounds, we were able to generate all trail cores up to weight 84. And we found trails of weight 80. So we have a tight bound for 4 rounds, while for all other number of rounds, we generated all trail cores with weight below these values, and these spaces were all empty. So we got these lower bounds. And notably, for 6 rounds, that's the number of rounds used in ZOOF, we have a bound of 132. And for 12 rounds, that's the number of rounds in Zodiac, we have a bound of 264. Then, so we looked more closely to these trail cores of weight 80, and we noticed that they have a particular behavior, so a predictable actually behavior through the rounds, and we use them to provide upper bounds. So to conclude the presentation, I wanted to show how these trail cores look like. So you can see here I reported the weight through the rounds, and you can see how it grows regularly. In fact, so the weight depends on the number of active columns in the states BI plus, the number of active columns in the state A1. And we can see that we start from 4 active columns, and then we go to 8, 12 regularly. We add 4 to each round, going in the forward direction. And similarly, we have this trail core where actually the number of active columns grows by 4, going in the backward direction. And that's all. So just to summarize, we introduced some optimization to improve bounds for Zudo, and we discussed these special families of staircase trail cores that allowed us to provide upper bounds. Thank you for your attention.
Thank you for your nice talk. Are there any questions or comments? Regarding the experimental result in your paper, so I guess the provided trail core searches are extended in either backward or forward direction. So is it impossible to extend it both directions at the same time?
So what we do is a sort of, yes, combination. So we start from 2 rounds, then to cover the wall space, we extend in the forward direction and then in the backward, and then we combine the results to see which gives the better bound, the lowest.
Okay, thank you.
Thank you.
Are there any other questions? Please.
Hi. So the results you had, so how heavy was the computations? How much time and memory do you need?
Yeah, I don't remember now by heart, but it took a few weeks. So in the paper we reported all the time for each single step, but yes, still it was quite expensive.
It's heavy. Okay.
Okay, I have one question. Thanks for your talk. Yeah, yeah.
Ah, sorry.
Yeah.
Yes.
So I mean, is it efficient with this tool to find some clean generating trail?
Sorry.
I mean, to find a trail that we can use for clean attacks, is it efficient to use this tool?
Of course, no.
Of course, okay.
No,
Very
as I said, it still takes some time to run, but what we saw is that this kind of dedicated tool is much more efficient than the SAT solver or MILP based tools. But still, yes, it takes some weeks to run and get good results.
Okay, thank you very much.
It's time to move on to the next talk. So let's thank the speaker again. The second talk is about the paper entitled Related Key Differential Analysis of the AS. The authors are Christina Bora, Patrick Delbet, Margot Funk. So the speaker is Margot Funk. Please give your talk.
Thank you for the introduction. So I'm going to present a joint work with Christina Bora and Patrick Derbez, and it's about the security of the AES in the related key model and against differential attacks. So the AES is the most used block cipher today. It was designed by Johan Damon and Vincent Ryoma and standardized in 2001. Its block state can be seen as a 4x4 matrix of bytes, and it is transformed by iterating a run function. This run function is composed of a nonlinear layer of S boxes, and then the linear layer shifts the rows, multiplies each column by a MDS matrix, and adds the round subkey. And also note that there are 3 versions of AES for 3 different key sizes. So the AES was designed with mathematical arguments to resist linear and differential attacks. And it is very easy to have a simple proof that every 4-round differential tray has at least 25 active S boxes. And since the maximal differential probability of the AES S box is 2 to the minus 6, this directly proves that every tray have a low probability. But unfortunately, this proof doesn't work in the related key model. So in this model, the attacker can also insert differences in the key. And it was shown that the AES is much weaker in this setting, with, for example, the discovery of an attack by Birukov in 2001 against the full bigger versions of AES. So after the discovery of this attack, it was important to find the optimal trace in this setting, but it's more difficult because obviously the search space is bigger. So several works tackle this question with different methods. They all start by searching from truncated trails with few active S boxes, and then they try to instantiate the trace. So the first approach was a branch and bind algorithm, but it wasn't very efficient. Then Fook and his co-authors proposed a dynamic programming algorithm, but it worked only for AES 128. And it is only in 2020 that an algorithm working for all versions of AES was proposed. So for that, Gero and his co-authors models the tray with a constraint programming model and use a solver to find a solution that maximizes the probability of the tray. So this work shows that solver-based tools can be efficient to solve this problem. But the problem with this kind of tool is that it is hard to understand their complexity. And this is why we wondered if it was possible to find the same bound without using a solver. And also in the case of the AES, because it's a very important target, it can be important to find the same bounds with an alternative method, especially considering that bugs have already been found for some solvers. So our main contribution was to extend the dynamic programming algorithm for all versions of AES. So before explaining how we did that, I want to explain some properties of the AES differential truncated trace. So because the AES has a byte-oriented design, we have very basic propagation rules at the byte level. So for example, to propagate the differences through mixed colon, we just use the MDS property of the mixed colon matrix. But the problem with this rule is that they lead to many truncated traces that cannot be instantiated into actual trace. Indeed, if we concatenate two truncated traces that can be instantiated, the concatenation can have an inconsistency. So here, for example, the left part of the tray is instantiable, so as the right part. But for the right part to be instantiable, some bytes must be equal. And if these bytes are equal, the right part is not instantiable. So there is an inconsistency. It is sometimes possible to detect some inconsistencies by considering linear relations induced by the round function and the K-schedule. And in our work, we consider that a truncated tray is valid if it is not possible to express a variable assigned to active as a linear combination of variable assigned to passive. And this is something that is very easy to check. We just perform linear algebra with a matrix in row echelon form. So when we search for a truncated tray, we can start by only considering some inconsistencies that often happen. And one type of inconsistency is linked to the key schedule. So for this presentation, you only need to know that the key schedule works by column. So for example, to obtain the first column of Ki plus 1, you just add the blue column with a nonlinear transformation of the red column. And for the other columns of Ki plus 1, they are just the XOR of the two other columns. So this is why we can derive linear relations from the key schedules between distant subkeys. And those relations are not taken into account by the basic propagation rules. So that can lead to inconsistencies. Also, I'm going to explain another type of inconsistencies by taking a small example. So here, by definition of the key schedule, the colon K2 is the sum of the colon K0 and of the colon K1. And if you consider those equations involving K0, K1, mixed colon, and add one key, and if you add them, you obtain new equations. And this equation gives you new constraints. Because from the MDS property of the mixed colon matrix, we know that in a colon before mixed colon and after mixed colon, the number of active bytes should be 0 or greater or equal to 5. And the problem is that in a model, when we encode only the two equations on the left, at the byte level, they are not combined automatically. So in other words, only the encoded equations are taken into account and not the whole vector space spanned by these equations. So this is an issue, and that's why in our dedicated algorithm, we targeted this type of inconsistency. So now I can explain our algorithm. So the starting point of our work was the work of Fook and his co-authors, but their algorithm was only applicable to AES 128, and the main limitation was the memory complexity. So in our work, we extended this algorithm for all the versions of the AES, and we were able to obtain a running time that is comparable to that of the constraint programming approach. So the idea of the dynamic programming algorithm is to represent in a graph all the trays. So here, each cross represents a difference that includes the block state and the key. And each arrow represents a possible transition through a small step function. So for example, you can think of a step function as mixed colon or the computation of a new subkey colon. And note that we have to put in this graph all the truncated differences and for all the steps. So there are many trays that can reach one given difference. And the value that we want to compute is the minimum number of active iceboxes needed to reach that difference. So in this random example, for example, this difference can be reached by three trails. And among them, the green one has the least active iceboxes. And this is this quantity that we want to compute. So there exists a very simple way to get these values for all the truncated differences and for all the steps. So assume that we already know this quantity for one step. We can use them to compute the quantity associated to the step just after. So for example, you can see that these cells can be reached by 3 transitions, and we need at least 6 plus 1, at least 7 active iceboxes to reach it. So the main advantage of this technique is that the time complexity is linear in the number of rounds. But for the memory complexity, we need to store arrays of size the number of truncated differences. And that's why we cannot directly apply this algorithm for the bigger versions of AES. So to give you an idea, for AES 256, that would require 256 terabytes to store one array. So to adapt this algorithm, we first reduce the memory complexity. And for that, we used a more compressed representation of the differences for the block state and the key. So we only specify for each column of the block state and the key the number of active bytes. And so as you can see, the resulting arrays are quite small. And this choice of compact representation is mainly motivated by the fact that the key schedule works by columns. So before that, we tried to only specify 3 out of the 4 rows of the state and the keys, but that didn't work. And also another issue to address is that the dynamic programming algorithm doesn't integrate constraints over several rounds. And this is why we decided to integrate them in a second step. So note that because we use a more compressed representation of differences, we lose information. So our propagation rules are less precise, and that introduces new incompatibilities. So we remove these incompatibilities during the second step. And also, we improve a bit the time complexity to compute the arrays. So in general, if you want to compute the value associated to a difference y, you need to loop over all the differences x that are compatible with y. So to loop over all the predecessors of y. And the naive way to compute the entire array is to do that for all the cells. But in fact, for some values y and y prime, and for some step function, y and y prime share the same predecessors. So we don't need to recompute the value twice. We can just take the value computed for y to put it for y prime. And also sometimes the predecessors of y prime can be expressed as the union of x and the predecessor of y. And also in this case, we can do less computation by just reusing the value computed for y to compute that of y prime. So after the dynamic programming phase, we need to reconstruct the truncated tray. And this step is mandatory because the bounds in our array can be lower than the real bounds because they don't take into account constraints over several rounds. So to search for a truncated tray with n active iceboxes, we first collect all the compressed tray with n active iceboxes. And for that, we perform a tree traversal in the backward direction. So for example, if we want to search for a tray with 22 active iceboxes, we start with a cell with less than 22 active iceboxes, for example, 18, and we extend the tray backward. And we use two criteria to prune the tree. We prune the tree if the number of active iceboxes is too high. So here, for example, we prune the tree because 20 plus 5 plus 2 is above 22. And we also prune the tree if we detect some linear inconsistencies. And in fact, because in a compressed tray, we can locate some active or inactive bytes. For example, when a colon is fully active or fully passive, we can detect some inconsistency, at least partially. And because the best trays are very structured, with lots of active colons or inactive colons, we can detect like that most of the inconsistencies. And also in this step, we targeted the type of inconsistency with mixed colon and adverb key I've presented earlier. So here you have the time complexity and the memory complexity to construct the arrays. So the letter R refers to the number of rounds. For the memory complexity, we chose different trade-offs depending on the versions of the AS. So the more arrays we choose to store, and the easier is the phase that reconstruct the trays. So for AS 128, we divide a round into 9 steps, while for the other versions, we divide a round into 3 steps. And finally, the total complexity depends on the number of trays found during the second step. So here you have a comparison of the running time of the CP approach and of our dedicated algorithm. So note that for the constraint programming algorithm, it also includes the instantiations of the trays, truncated trays. So our algorithm is parallelizable. So in red, you have the time when 8 cores are used. The main objective of our work was not to gain few seconds or minutes. It was mainly to show that it is possible to find the same bounds without using a solver. And also, maybe our work gives more insight on the properties of the truncated trays that have few active iceboxes. So for example, for AS256, we noticed that the reconstruction of the tray was very fast. This is because there are very few inconsistencies. While for AS192, there are a lot of inconsistencies coming from the high linearity of the key schedule. And this is why, for example, for 9 rounds, our algorithm is much slower than the constraint programming algorithm. So to conclude, I've presented an ad hoc algorithm that can compete with solver-based tool. It works well because the AES is very structured, and it shows that the search space is much smaller than one could have expected, especially for AES 256. But for less structured ciphers, it seems hard to adapt this technique. And also to compare our algorithm, we introduce a MIP model, and we also built on top of our MIP model an automated tools to solve for differential middle attacks. And we were able to find the first attacks with only 2 related keys against 30 rounds of AES 256. So thank you for your attention.
Thank you for your nice talk. Are there any questions or comments?
So, hi, thank you for the talk. So, as far as I understand, that dynamic programming is not only the reason for this time improvement. I think better representation of the constraint and compressing information is also helped here, and it was effective. So, I was wondering, If we try to create so this better constraint and try to create constraint for CP program and throw it on a CP solver, will it be still slower than previous CP based approach, or did you think about this direction? I mean, my point is that these constraints are also smart than previous constraint. So not only dynamic approach helped here, the constraint also helped here to get better efficiency, right? I mean, first of all, okay.
In fact, we only added the constraint during the second step, but I don't know if it's your question or.
Okay, so let me ask you again. So to get this better efficiency, does the constraint also help? Or only dynamic approach helped here?
For in our dynamic algorithm or in general?
In general, I mean, you
general?
represented the.
In general, for example, the constraints for the key bridging is very helpful for AES 192, but it is less useful for AES 256 because there are. So it depends, for example, on the versions of AES.
Okay. Thanks.
Are there any questions? So, okay. The running time for AS 128 is presented only up to 5 rounds.
Yes.
So, if possible, could you tell us how many, the maximum number of rounds that your proposed attack can execute in a realistic time?
I think we tried for 6 rounds and not above, because after that you have enough active S boxes. But I did not know the running time.
Okay, thank you. Okay, it's time to move on to the next talk. So let's thank the speakers again. The third talk is about the paper entitled Finding Impossible Differentials in ARX ciphers and weak keys. The authors are Chen Ling, Tintin Tui, Fan Tao Fu, Xija Gong, Dijun Fei, Jari Fan, and Jia Xiao. The speaker is Tintin Tui.
It's open.
Okay, please give your talk.
Yeah, thank you. Yes, my name is Tintin Cui. My topic is finding impossible differentials in ARX cipher and weak case. Oh, I'm sorry, this is not the new one, but yeah, as we know, impossible differential is the one of the most important methods in the symmetric ciphers. And there are 2 ways to find impossible differentials, as we know. The first one is we treat the S box in the cipher as idle ones, so that we can find some impossible differentials such as the U method, UID method. And the second phase is we use some automatic tools such as to based on MILP, SAT, SCP, or CP. But all the methods based on 2 underlying assumptions. The first one is the Markov cipher assumption, and the second one is K-dependent assumption. But as we know,
Nowadays, the design trade of ciphers is lightweight, more light round function, more light key schedule. So is the markup be used correct in it? I think so. Let's take an example. For in ARC cipher, there are two consecutive modular additions, and the Markov cipher assumption, it is possible in the left and right, and we divided them up. But if we don't care about the Markov cipher assumption, we found that this differential pattern is not possible. So we would like to do some work on the impossible differential attack and some weak key without the Markov cipher assumptions. First, we found a property on single additional modular 2 to n. The first one is given by Li, and they found that if both the L bit of delta x and the delta y is 1, then the output differential delta z is 0 if and only if xl do not equal to yl. And in our work, we inverse found some property on the modular minus. If delta y and delta z has one nonlinear non-zero on the L bit, then delta x equals zero if and only ZL equals YL. And these properties are used in the proof. Then we found some properties on two consecutive modular additions. This is the first one, delta x, delta y, delta g input difference, and the delta h is the output difference. This is a possible differential, but when delta z 2 to 1 is not 0, 0, the differential will become impossible. Yes, it is weird. Delta z 2 to 1 is cannot be controlled by us, but from the experience, we found if we fix the input differential and the output differential, this construction on the internal state will happen. And more one, this is another property, delta x, delta y, delta j are the input differences, and delta h is the output differences. This is impossible one. Please note that the differential are truncated, so we can extend by under some uncertain bit on the lower positions and the higher positions. And another one is like this, but this is happen on F2 4. It can be extended to F2 5, and it also impossible. Why we found these properties? Yes, this can be used in the practical ciphers to find the more complexity constructions. And we only introduce 3 property on 2 consecutive modular additions here, but we found more impossible patterns, about thousands. But because we only use these three properties in spec on CHAM, so we only introduce them here. And the more we put the code and the result on the GitHub, if you have interest in it, you can find that. And we hope to apply these properties on ARC ciphers, and we found that there are 4 local constructions extracted from the AR ciphers, like in the picture, to consecutive modular addition, or put rotation in the middle, or XOR with a secret key or with a constraint. Yes, for the first construction, we apply the properties 3, 4, and 5 on them, and directly we found some impossible differentials on the local construction. And with the rotation in it, it will not change any result, and we can easily to put that. But if we put a security key here, we found that not always case make this happen. Only in some weak case like this, according to property 4, K2 plus 3 to I plus 2, when this 2-bit key is 00 or 111 or 11, the IDs will happen. And the similar, if there is a constant here, and we need put some constraint on the constant so that the IDs will happen. Yes, we also found some properties on the 3 consecutive modular additions. It's a little complexity. So just like this one, this is delta X, delta Y, delta D, delta Z, never lead to delta H like this. This is a truncated one. And we can also put some rotations and some K or some constraint in the middle of the modular additions. And we found 3 more complete impossible differentials on this. Yes, please note that some K bits must be limited, or some constant must be fixed. So with these properties, we found a framework to find IDs in AR ciphers and weak keys. In the first step, we also like the traditional impossible differential methods. We obtain truncated differentials from delta xi to delta xi plus m, and delta xj to delta xj minus n by some tools. In the second step, we check if there is a contraction between delta xi minus and m to delta xj minus n. If so, we found an impossible differential like the traditional method. But if not, we use some tools to obtain some possible forms of intermediate differentials on delta x I plus m plus t, and divide this part into two and use some weak keys to delete the all possible patterns so that we can also find impossible differentials. Yeah, yes, with this framework, we apply to SPEC, to LEA, and the CHAM. This is 8-round impossible differential for SPEC and 2 to 60 weak case. And from it, we can see that in the first round, we use the property 1, and the 8th round, we use property 2. Then in round 2 and 3, we use property 4, and round 4 and 5 we use property 3. Then we apply it to LEA to find 11 round impossible differentials and weak K2 to K plus K minus 1. And we also use to the CHAM to find 22 round impossible differentials and weak K about 2 to 127. Yeah, this is the result. And from the table, we can find that our impossible differentials are more longer than the previous ones. So in this work, we found some more accurate differential properties on the molecular addition and a framework to find the impossible differentials and the weak key. And we apply it on some ciphers to find the longer impossible differentials. But there are also some future work. For example, the property 3 to 6 only a selection of the impossibles found by experience. There are also thousands of impossible differentials, but we cannot summarize them to the truncated ones. So it's possible to continue analysis these IDs. It's also meaningful to try to build an automatic search model. Yes, we are doing this now, but we have ideas. We do not have ideas how to do that. And also it's worthwhile to find some impossible differentials to get better key recovery tags. You know, the longer impossible differentials do not mean longer, do not mean better key recovery attacks. So we need some better ones suitable to do some key recovery attacks. Yes, that's all. Thank you.
Thank you for your nice talk. So are there any questions or comments? I have a question. So regarding local conditions or local constructions. So I think 3 operations and rotation x1 should be generally included between 2 consecutive additions. So could you tell us why you didn't consider a local condition, local construction involving 3 operations? Please show us page 8.
Page 8. This one?
These constructions.
Yes, these 4 constructions are extended from the EX ciphers. Yes, and there are many other constructions, but we only use these 4, so we show this.
Okay, Thank you. Are there any other questions? Okay, so it's time to move on to the next talk. So let's thank speak again.